Hello, can you hear me? Oh, thanks for inviting me to speak about this topic. What I'm going to tell you today, the most of what I'm going to tell you, it comes from a paper that is recently been written, and the author list is here on the bottom, called Rings and Radio Waves in the Disk of the Milky Way. And a lot of the heavy lifting has been done by Xian, who is the first author of the paper. So all the plots that you will see that have to do with this are things that she drew. Of course, I did the artwork, but she did the science plots. Okay. So what I'm going to do, I'm going to spend a few minutes at the beginning reviewing Milky Way halo substructure. I'm not going to get to all of it. I'm particularly going to emphasize some of the things we know about substructure that's near the plane of the galaxy and that has been controversial for more than a decade. So I want to kind of review that a little bit so you know where we're starting from. And then the crucial thing, so if you fall asleep now, here's the thing you don't want to lose, is that, how do you operate this? I guess you have to make this part point in that direction. Here we go. The important thing is that the midplane of the Milky Way disk oscillates up and down as viewed towards the anticenter. So if you're at the sun and you're looking away from the galactic center, the disk goes up and down and up and down. That's not to scale. But this is the idea. The disk goes up and down and up and down. Okay? That's what you're going to take away from this. And so a lot of this talk is going to be, I'm going to convince you that that's the case. All right. And then I'm going to put that in context of what these disk oscillations mean and have a conclusion. All right. So starting with lumps in the Milky Way. So you want to trace the density of stars in the Milky Way, and you're going to look at a halo, so you have an old population. So here's a globular cluster, and this shows you all of your choices for tracers of the halo, because these are all the stars that are out there, and you can't really see the faint ones down there very far away. Okay? And of all of these tracers, the ones that I have liked the most are these Turnoff stars, because there are a lot of them. They're the brightest of the main sequence stars you can get. When we started using these, astronomers thought these were the most horrible things to use as distance indicators, because this is like more than 2 magnitudes from there to there, that they can have a 2 magnitude range in absolute magnitude, which doesn't make them very good distance indicators. But when you've got millions of stars, you can kind of average it out and figure out where the middle of the distribution is, so you're okay. So you can use something called statistical photometric parallax. One of the things that I did not know when I started using these, and it turns out to be a great boon for these turnoff stars, is that if you look at the age-metallicity relationship for the Milky Way, there's a conspiracy in the age-metallicity relationship for the Milky Way that all of the old metal-poor populations of stars have the same mean absolute magnitude of turnoff. So the older stars are metal poor, and older makes the turnoff fainter, but more metal poor makes the turnoff brighter, and they cancel exactly. And so all the metal populations that have metallicity -1 and lower, this kind of stuff you have in the halo, the turnoff stars are pretty good distance indicators in a statistical sense. Not on an individual star sense, but in a statistical sense in terms of getting distances. And so a lot of what we have been working on in measuring halo substructure has been, it turns out, in turnoff stars. Now you're going to get this picture because this is my most famous picture that we ever made, right? This is what I'm known for. This is the discovery that the halo of the Milky Way is lumpy. And what is this? This is a density map of these turnoff stars selected from the equatorial stripe of the Sloan survey, because at the time all we had was an equatorial stripe. Okay? And so you're here. This is apparent magnitude of turnoff stars going out, so they get farther and farther away as you go out here. And this is distance around the equatorial stripe, and this is where you go through the galactic plane on deck equals 0. Okay? Now, when we made this plot originally, it was a huge eye-opener, because we were trying to use this data to fit a smooth power law, partly squashed, whatever, halo distribution to this distribution of stars in the halo, and there was no possible way to do that because there's a big lump here, and there's a big lump here, and there's a big lump here. Forget this, this is just a dust mot. There's actually a lump over here and a lump over there and lots of stuff going on that does not look anything like a power law. So this is the discovery that the halo of the Milky Way is lumpy. And here are some labels that we can put on these things now that we've discovered what they are. This is the Sagittarius tidal stream right here, Virgo. I'm going to talk a lot about the stuff that's towards the anticenter, the Hercules Aquila clouds there. So a lot of the major density substructures of the halo you can see here. Yeah?
Is there a scale in kiloparsec?
Yeah, this is like 40 kiloparsecs. It goes out to like 40 kiloparsecs, 40 to 50. Okay? From the sun. Okay. So, all right. So let's start out with this one, because this is one of the first ones that we had any idea what was going on. This, by the way, is a globular cluster, and you can see in how much these stars are spread out in apparent magnitude here. They're actually all at the same distance. So this whole image is sort of convolved with something about that big in the distance range. Okay, and so you have to take out that if you're going to look at it as a density map. All right, so I'm going to look at this purple structure. So if I look towards this direction over here, and I make a Hess diagram, actually this is a subtracted one, you see that this is the Sagittarius dwarf galaxy. I'd say the ghost of Sagittarius. There's the horizontal branch, the giant branch, the turnoff, and blue stragglers, like you would see from Sagittarius. And what that lump is if you haven't seen this very famous old picture by Kathryn Johnston, why is it not playing? I have to click on it. Okay. Why is it not going? Oh, here we go. This is a model of the Sagittarius dwarf going around the Milky Way, and as it goes around, the stars are tidally stripped down into these big long streams as it goes around the Milky Way. And what we had done in the equatorial slice is we sliced right through it, and it went right through the slice. There's the Sagittarius going through in the north and Sagittarius going through in the south, and so those two lumps from the wedge plot were in fact pieces of that same stream. Okay? So this is the origin of these lumpy things that we find out there. This is a more modern picture, slightly more modern, halfway back in time, done by Vasily Bellick, very famous picture. As again, Sloan Digital Sky Survey, but now instead of just having this one equatorial stripe down here, we have the whole North Galactic cap, and these are color-coded, so the closer ones are blue and the farther ones away are red. And you can see this is, again, turnoff stars, basically, a density map of turnoff stars with colors indicating average distance in that direction. And so here's the Sagittarius stream going all the way across the sky. Here's the orphan stream, so named because I don't know where the dwarf galaxy is that made that. Here's a Hercules Aquila cloud. Here's the PAL 5 globular cluster in a big tidal stream. And this is something we're going to talk more about, the Monoceros Ring down here, all this closer stuff towards the galactic anticenter. Okay. This is a recent picture done by Karl Grimmer, who has the same data, except on here he's drawn the positions of a whole bunch more little streams that have been found in the Sloan Digital Sky Survey by going looking in finer and finer detail. And so there's lots and lots and more streams, smaller streams that are being discovered in addition to these really big ones that were discovered before. And this was made for this upcoming Springer book, Tidal Streams in the Local Group and Beyond, which is edited by Newberg and Carlin, which you should look for sometime in the near future. It's just about finished, so I'm just plugging that if you want to learn more about this. Okay, so now I told you I was going to concentrate more on what happens at the anticenter. I want to talk about this thing here because at the time we made this picture, this, to us, we had just figured out what that was, right? This is a Sagittarius stream. And then you say this thing over here. Now this is about 11 kiloparsecs from the sun towards the anticenter, which makes it like 18 or 20 kiloparsecs from the galactic center. Beyond the disk, right? Because the stellar disk is supposed to go out for 15 kiloparsecs. And we looked at this, and we said, oh, this looks to us a lot like this over there, so it looks like there's another stream near the plane of the Milky Way galaxy. Okay, and if you look at a color magnitude diagram for that, you see there's this narrow main sequence down here, and then maybe this is all at different distances because we're looking through the disk or something. Maybe, I don't know. But this certainly doesn't look like it's part of the disk. This is a narrow main sequence, all the stars at the same distance. Okay, so again, still looks like a tidal stream. And why is it called Monoceros? Well, because in this original paper we found some over here. The red data was actually available at that time. The rest of the Sloan data was not. But we found it here, we found it actually over here, we found it actually in all the pieces near the plane that we said, and kind of in the middle of this was Monoceros. And we didn't really know how to name it because it covered the whole anticenter, and we didn't know exactly what was attached to what or what it looked like down here. I mean, this is completely unknown. That's what it is. Here's an artist's conception of the thing. Here's a galaxy, and here's one version, and this is clearly a tidal stream. There is a claim that there's a dwarf galaxy in the plane of the Milky Way over here in Canis Major, right next to Monoceros, that was thought to be possibly the progenitor of this tidal stream. More stuff towards Andromeda was a bunch of stuff out here found called Triandromeda stellar stream out here, which could have been attached to it, and lots of other pieces of debris in the plane of the Milky Way were also found. And pretty much at that time, anything that was found near the plane of the Milky Way was ascribed to be must have something to do with Monoceros, right? Because my original name for this in the paper that, we had named all of these things, S223 plus 20-19.4, which is the L, a B, and the apparent magnitude of the turnoff, seemed like a reasonable thing to say, but nobody could say that. And so since then, everybody has been coming up with their own name for it. So it appears in the literature as Monoceros stream, the Monoceros ring, the stream in the galactic plane, the galactic anticenter stellar stream, which is gas, which I particularly don't like because I don't like to have found gas in the plane of the Milky Way. But anyway, so there's all kinds of different names that have been ascribed to this. And this dwarf galaxy is pretty controversial even still. I actually don't think it's really a dwarf galaxy because what they see is they see an overdensity in the direction where there's less gas in the disk of the Milky Way, so they kind of see through the gas there. And so the question is there really more stars there like there's a dwarf galaxy, or you just see more? And there was a claim that instead it was over a bigger region. It was called Argo Navis, and so all these different things have been found and not really understood. So the explanations for this ring or the stream or what's found out there, one or more pieces of tidal debris, which could have puffed up the thick disk or could have become the thick disk itself. There are papers that have put those forward. It could be a warp flare of the disk or a spiral arm in the disk. There's a possibility it could be dark matter caustic from axions, and it's all different reasons how this could be. None of these so far have really worked out as an explanation, and I'm going to show you an explanation of what I think. Here's another artist's conception. This one is more ringy and less like a tidal stream. So there's another artist's way of looking at the data. Maybe it comes out like that. Now, one thing that I wanted to point out about this, in the literature, this is a figure from Newberg et al. 2002, okay? And this is the piece of the Monoceros that we found in the south galactic cap. So it's at B equals minus 24. And there is a main sequence here, and we figured this must have something to do with the disk. There's a gap. There's this Monoceros structure, okay? In Bada et al. 2003 paper, also in the south, they found this picture, and you see in green, they ascribed this part to Monoceros. Because if you actually compare this distribution with any of the models of the Milky Way stellar distribution where it ought to be. This doesn't fit it. There's too many stars down here. And so they said that was Monoceros in the south, and we said this is Monoceros in the south. And so in the 10 years or more since two papers at the very beginning gave different identifications for what was Monoceros in the south, there's a lot of confusion. Some people call this Monoceros, some people call that Monoceros. This is actually at higher galactic latitude, and this is at lower galactic latitude. So then a lot of times at lower galactic latitudes, people claim that's Monoceros, and at higher galactic latitudes, this is Monoceros. And at these, and here you can see there's an extra main sequence down there, which is usually called the Triandromeda stream, or the Triandromeda ring. So, so there's a lot of confusion in the plane. Okay, if you go back to the wedge plot, because I keep going back to this, this is Monoceros in the north, and if you follow this over at the same magnitude in the south, it's closer to this one, which is what we called Monoceros in the south, but it's actually, this is a little further away than that, and this one over here is closer. And so they said, okay, well, I'm going to connect it from here to here, and we said, I'm going to connect it from here to there. And that was the difference. Okay. This is a picture looking towards the galactic anticenter, again using main sequence stars, where bluer is closer to us and red is farther away, taken with pan stars. And so what you can see with pan stars now filling in a lot of the stuff between what we had originally, that there's extra stuff kind of all over the place near the galactic plane. From this, it looks like the south is a little closer, but, you know, it's hard to know what's going on. And one of the things that you should really see here is there's a lot of filamentary, kind of wispy, like there's a lot of stuff going on there near the plane. There's a lot going on there. Okay, exactly what it means I can't tell from this picture, but there's a lot going on. All right, and it goes all the way through the plane, and it's pretty much everywhere in that direction. So the streams or clouds that have been discovered and named near the plane of the Milky Way, in the north we have the Monoceros Ring, the Anticenter stream, which is this right here, which may or may not be related to the Monoceros Ring, the Eastern Banded structure, which is over here. These are all at the same distance, right? So they're near each other, but have a different structure. And in the south, there's the Triangulum Andromeda stream, the Canis Major Dwarf Galaxy, Triangulum 2, the Pandas Milky Way stream, and the Pandas Northeast Blob. And I wanted to show you some data from those. Here's a recent paper by Sheffield et al., which shows you, again, this is following this is Monoceros up here, and that is Triandromeda, and they actually see another one down here, which they call Triandromeda 2, which is a little bit farther away main sequence. And then I also have this paper from Pandas, which is looking towards the Andromeda Galaxy, but scoops up some of the Milky Way on the way there. And they have, following Ibada, called this Monoceros. Okay, and if you look at the density on the sky of the stars in this strip, you find that closer to the plane you find more stars. And then this second region over here, you don't find too much. If you go to the third region, where this is Triandromeda, you see these wispy structures. And if you go down to this fourth region, then you see what they're calling Triand 2, is this little blobby thing. And then this is an unrelated tidal debris stream from presumably a globular cluster. And so as they cut the data in different distances away from us, they see different structures and wispinesses on the sky. Okay, looking at stuff in the galactic plane. Okay. Now I want to go back to this blob right here, which I have a question mark right there. And I've had this slide for many, many years, and it's had a question mark on it for many, many years. And I've told people that, when we published this paper, we tried to fit the disk, the thick or thin disk or some combination of it, to this blob over here. And it sort of works. in the sense that if you make a disk structure with a reasonable scale length and scale height, it does put some stars about in that place, but it doesn't match the density distribution very well. And I never thought that, this is a little bit too localized in distance to be a disk, and I've known that for a very long time. And when Xian came to work with me, I said, Xian, why don't you look at this and figure out why that looks like that, to see if the disk, if you really can get the disk to fit that. Can you get the disk to fit that? And so what I'm going to show you now is what we came up with on how well it fits. So in the many years it's been since the original paper, there's been a lot more Sloan data, and in fact we took some data that goes right through the plane here. And so what I can do is I'm going to compare, I've got these, I'm going to show you these 5 stripes of data that go through the plane. And I've divided it up into 2.5 degree little boxes. So I've got all these little boxes in the north and then the corresponding box in the south. And there's boxes in the north and boxes in the south. And I'm going to make color magnitude diagrams in each one of these little directions in the sky. Okay? And I'll show you this plot because you're not going to be able to read the numbers on the plot I'm going to show you next. So get ready. What you're looking at is in the north, you've got 5 stripes that are straddling the galactic anticenter. And you're going to have 1, 2, 3, 4, 5, 6 different galactic latitudes along each of those stripes. Okay? Or maybe there's a few more. Anyway. 1, 2, 3, 4, 5, 6, 7, 8 of them. All right, I didn't make enough boxes on the last plot. Okay, so these are 2.5 degree things. This goes from 30 degrees plus 30 to 10 degrees above the plane. So the galactic plane is here, and we're going north as we go down. And these are color magnitude diagrams. And they look a lot like the color magnitude diagrams that we had for the Monoceros stream. Okay? There's some stuff up here, which you say, oh, probably some disky stuff. It's kind of over a bunch of different apparent magnitudes, so probably kind of a range of distances there. Then there's a gap, and then there's looks like a stream, Monoceros, with a bluer turnoff. Okay? And each one of them, kind of some disky stuff, then a gap, then a stream. Kind of some disky stuff, then a gap, then a stream. Disky stuff, then a gap, then a stream. And down here, there's a lot of gas and dust, so this gets kind of smeared out some. But then a gap, and then a stream. Disky stuff maybe, then a gap, then a stream. Pretty much, wherever you look towards the galactic anticenter, it looks about the same. And so what you're seeing is that there's this Monoceros structure is over the whole galactic anticenter area, and this other structure, this kind of disky, possibly disky thing, is over that whole area, and it looks pretty much the same no matter where you look. Okay. Now I'm going to do the same in the south. So this is minus 10 galactic latitude, and this is minus 30 galactic latitude, and these are the same galactic longitudes that we had before. And in the south, you see there's kind of a disky thing, and then a gap, and then what looks like it might be a stream. Kind of a disky thing, then a gap, then looks like it's a stream. Not too much data there. This is in the direction where the triandromeda, this was the triandromeda thing we had down here. Kind of a disky thing, then a gap, then the stream. Kind of a disky thing, then the gap, then the stream. And so we called this bottom thing Monoceros. Over here it's been called triandromeda, but, whatever. And now I'm going to do something which hopefully will change your whole view of this whole problem, because after a very long time looking at it, eventually that's what changed my view of the whole problem, which is that I'm going to take all of the color magnitude diagrams that I have from the north, and I'm going to subtract the color magnitude diagram from the symmetric point in the south. Okay? And if the galaxy is symmetric from north to south, it will be flat. Right? Okay. So now I'm subtracting them, and it's not flat. It's skunk plots all the way. All right? Little stripes. Now, if it's white, the white main sequences mean there are more stars in the north. The darker main sequences mean there are more stars in the south. And so what you find is there are more stars in the north, then more in the south, then more in the north, which is where we originally found Monoceros, and then if you go far enough down here, you know, the statistics aren't too good, but you could tell in the other one there were more in the south. Okay? More in the north, then more in the south, then more in the north, then more in the south as you go out, and that pattern includes Monoceros, includes Triandromeda, if that's what you called it, and it includes these two other oscillations that are in front of it that we've always been sort of ascribing to the disk, but never really fit very well. Okay? So, you know, if you're a stream person, you're like, oh my God, does it mean there are 4 streams? If you're a disk person, you're saying, oh my God, it's like the disk is doing something funny. All right, and it starts a lot earlier than Monoceros. Okay, now some of you, I know, are going, can I get this because of the reddening? Is reddening screwing this up somehow? And it's really, you know, reddening, it was pretty easy to decide that this was because of reddening when we were just looking at those turnoff stars, because who knows what the reddening's really moving stuff into and out of the turnoff, you know, hard to know really what's going on. But now that I've shown it to you in this way, the reddening vector is in this direction, and the main sequences are in this direction. And so if you get the reddening wrong and you push one of them too far this way, or not far enough, or something like that, it doesn't matter. These things are still going to give you white, and then black, and then white, and then black. And for those of you who need to see the raw numbers, we've taken all the stars with a G minus R between 0.4 and 0.5, so kind of turn-off stars, and we've given you the number of stars as a function of magnitude. And in the north, you see a big peak here, like 1,000 counts, and in the south, that big peak is moved over here. All right? And then in the north, you see Monoceros, and then in the south, you see Triandromeda, and there might even be another thing in the north. I don't know. Okay? So the star counts don't line up. And it doesn't matter which direction you do this in, they all do this. Okay? Doesn't matter which one. Okay, so what do? We can say, okay, we can fit an isochrone to this, and we can fit an isochrone to that. It's not so easy to fit an isochrone to this upper thing because it's kind of fat, but we did kind of fit something through the middle of it. What the heck? And we tried to fit isochrones that had the metallicities of the stars that were in each of these structures. This is like -1, and this is like -0.5, and this one's like -0.88 or something. It says right here, yeah, -0.88. You fit isochrones that kind of match the metallicities of the stars you find in these directions. And for these ones, we fit these crosses are peaks of vertical stripes that go through here. For this one, we did horizontal because the vertical, you know, gets kind of bad over here. But we, you know, said where are the centers of these, and then we just fit the isochrones through them and came out with a whole bunch of distances to each of these things. The other thing that we could do is then, now that we have an isochrone that's fit to this we call the north near structure, we can select out all the spectra. The spectra from Sloan are these points here. Select all the spectra that are consistent with being part of the north near structure. And then we can go in the south and use the same criteria where there is not a structure and choose the stars from there. And then we can go to this south middle structure and pick out spectra that are in the south middle structure, and then, south middle structure over here, and then go to the north and pick out stars that are at the same distance in the south as the south middle structure where the south middle structure isn't. And we can compare them all to each other. And I can't show you all of the plots that we made to try to compare all of these, but I'm going to show you a few of them. These plots are all metallicity versus VGSR, line of sight, galactic standard rest velocity. Okay? The ones up here are north of the galactic plane, and the ones down here are the symmetric position to the south of the galactic plane. So this is L equals 203, 178. I think I'm using up your battery here. And 110. Okay? And you'll see that the velocity changes with galactic longitude, which is what you expect for disk stars. In fact, they go exactly as you expect for disk stars. And the metallicity, these are all at about plus 15, and these are all about minus 15 galactic latitude. The metallicity looks like the metallicities of thin disk stars, which you would expect at that latitude, and doesn't seem to really have anything to do with longitude. And it's the same if you're in the north near structure as if you're in the comparison field for the north near structure, where the north near structure isn't in the south. So basically, if you're in one of these structures, you're not in one of these structures, it looks like the disk. It's exactly what you would expect for the disk. Okay? So here's some examples from the south middle structure, in this middle structure. And here I have a whole bunch of different galactic longitudes, but and I've put them in order of galactic latitudes. This is minus 26, minus 24, minus 22, minus 18, minus 15, minus 12. And you see as you go closer to the disk, the metallicities of the stars get higher and higher, as you would expect. As you go closer to the plane, you get higher and higher metallicity. So again, so up here we would call them thin disk metallicity, here thick disk, and here halo. So again, looking at the south middle structure, it looks just like the disk. Everything looks just like you expect the disk to. In fact, we took the predictions of the Shunrich and Binney dynamics calculations, which include the asymmetric drift calculations for the disk, and we fit this red line is the model. We fit the model prediction, no parameters, no free parameters. We fit that to the velocity distribution that we got in each of the panels where we had enough data that we could do it. And it fits perfectly. No free parameters. These stars are the disk. Okay? No question that it's streams or whatever. We tried very hard to make it be streams, but it is just the disk. It's exactly what these are, the stars we have been calling the disk forever. These are they. If you take the isochrones that we fit to each of these things and you plot them on the sky looking down on the galactic plane, so here's galactic X and Y, here's the sun, here's the galactic center is over here, so the center of these circles is the center of the Milky Way galaxy, and the X's tell you where we fit the isochrones, and the different colors are where the isochrones fits where at different latitudes. There's a lot of work here, right? All this stuff out, doing all this fitting. For the north near structure, we just sort of find circles kind of around the sun, and I think that's because we're so close to ourselves that we're just kind of fitting the disk there. We're not really fitting the distance to a structure. We're basically just finding here that there are too many stars in the north and the south, and what the shape of it is, I don't think we can tell from there. But as we go further out, we can see that there actually, it goes a little bit further away the more we go into quadrant 3. So here's the north near, the south middle gets a little bit farther away as we go to quadrant from 2 to 3. Monoceros Ring a little bit farther away as you go this direction. Triandromeda a little bit farther away as you go this direction. So they're sort of rings centered around the center of the Milky Way, but they open out slightly as you go into quadrant 3. Then we did a more complicated thing rather than just fitting isochrones to it, which is not such a great idea, because if it really is a disk structure, then you've got your volumes getting bigger and your densities going down, and so there's some combination of those on top of whatever distance you're getting. So a weird thing. So in this case here, what we did is we took an exponential disk for the thin disk, an exponential disk for the thick disk, put some reasonable values in there, and then tried to fit any values that we didn't know very well as best we could to the data to see how well we could get the star counts in each direction to match the model. So here the histogram, this dark histogram for each of these bins, and I sprouted some more because in this figure I have more galactic longitude ranges, but don't worry about that. This histogram is the actual star counts as a function of magnitude of turnoff stars, basically. And then the red gives you the thin disk model, then the thick disk model, and then the black line is the sum of the two. And you'll notice that the best fit model that we can get between this black line and the histogram basically doesn't, and the dotted means that we give it to you. We didn't actually fit the dotted ones because there were questions about the reddening or something in that data. Turns out actually it didn't matter at all. But you'll see that none of the black lines in the best fit model look anywhere remotely even like the magnitude distribution of the histograms, none of them. So no double exponential profile could be made to fit this. Okay, so we tried the following thing, make a toy model, and what we're going to do is we're going to, since we had more stars in the north, we're going to perturb the disk midplane up, and then we had more in the south, so we're going to perturb it down. And we didn't do the star counts out here because we start to lose completeness out there, so I don't want to do a star counts model out that far. So I only did the first two in the star counts model. So we just took the exponential disk and then we perturbed it up and down like that and did a best fit model again. Now, if you look towards the anticenter, we're actually not so bad in fitting the shape of the star counts towards the anticenter. But if you compare like the left and the right, it doesn't match at all. And you can see right away why we were unable to do this, because the model that we were fitting was axisymmetric, okay? And the data is not at all axisymmetric. This data over here has a little peaky thing here, and it's kind of flat on that side. And so in order to fit this model, we're going to have to do something a little bit more complicated than just perturbing it up and down. But certainly perturbing it up and down helped to fit it at least towards the anticenter. And you have to ask yourself, how much did we have to perturb it up and down in order to get the star counts to vaguely match? And the answer is 70 kiloparsecs, or it's not kiloparsecs, 70 parsecs up and 170 parsecs down. And so we're looking at an oscillation in the midplane of the disk of about that much in order to make it match. Okay. That's with the wave. Okay. Another thing is that the spiral arms, with this is from a paper by Ho and Han. It turns out, I think his name Ho. I think Ho was like downstairs when we were working on this at the NAOC. He came up and showed us his little plots. And if you look at where spiral arms are, and I know it's very difficult in this, I should try to get a better picture to do the comparison. But if you look at, here's a spiral arm and here's a spiral arm, they actually more or less line up with the north. This one lines up more or less with the north near structure, and the next arm out lines up with the south middle structure and opens out in the same direction. One of the strange things is if you look at the positions of the spiral arm tracers, masers and star formation regions and stuff, where we have a warp of the disk up, there are more spiral arm stuff below the plane, and where we have a down, there's more spiral arm above this. So the spiral arms seem to line up and go kind of in the same direction, but they're shifted in the opposite direction from where we're seeing the stars, which is a little bit surprising, but not actually terribly amazingly surprising. And I will try to explain why I don't think that's amazingly surprising, although how the disk and the gas, the stars and the gas really line up with each other, I'm not completely sure how that works. Not at all sure how that works. But they seem to be related in some way. And, I think I've actually seen these skunk plots for a couple years, and for a long time I just could not figure out what to make of them. I see them, I was like, yeah, but what sense does this make? It doesn't make any sense. I ask people, could this happen? No, this can't possibly happen. Okay. But in recent years, and this is a figure made by, how do you say it? Kazantsidis. Does anyone know spell it? Kazantsidis? I don't know how to say it. That is a picture that he's put out. And what he says is that if you have subhalos, dark subhalos or dwarf galaxies that go through the disk, they can turn something that looks like this into something that looks like that. Okay? And so these waves in the disk could explain the kinds of star counts that we're seeing. Okay, but this was 2008 that this started to come out, and I wasn't really paying attention to it in 2008. But since then, these are 3 papers in 2012 and 2013, and this figure here is from Carlin et al., that have found that there is velocity substructure, bulk velocity substructure in the disk. This has been found in RAVE. This has been found in the Sloan Digital Sky Survey. This has been found in LAMOST. So here's an example, and here we're plotting the velocity in the z direction, the average velocity in the z direction, and this is the height above the plane and angle on the sky looking towards the galactic anticenter. I guess this is the galactic anticenter right here, okay, from the sun. And stars that are up here above the disk appear to have velocity, bulk velocity down. Stars that are down here have bulk velocity up. Not something that you get in a standard model of the Milky Way. You don't get this from spiral arms. You don't get this from bars. You don't get this kind of a crunching thing. And there's radial bulk velocities. There's vertical bulk velocities. And exactly what they all mean, we've been scratching our heads. There have also been papers looking at Sloan data and star counts where they look at stars that are above the solar position, so looking straight up at 90 degrees galactic latitude and looking straight down, minus 90 degrees galactic latitude. Here's this blue line is a symmetric line, and then you have star counts. So what they showed is that the star counts, there are more counts in the north than the south at 1 kiloparsec above and below the plane, but if you go up here to half a kiloparsec, there's more in the south than the north. Okay? So there look like they're vertical oscillations in the density of stars above and below the plane at the position of the sun. And this is a paper from 2003. This is a movie made by Purcell, 2011, which his claim is that if the Sagittarius dwarf galaxy, which made that big Sagittarius tidal stream that I showed you in the beginning of the plot, plunges straight down through the disk, that you can excite these rings and wave structures and spiral structure in a galaxy. And so that could be an explanation for the kinds of things. It could be the Sagittarius dwarf galaxy itself saying this. Here's a movie that was made from using the Andromeda to try to understand Andromeda spirals and rings. And they had M32 going by and creating these kind of radial waves and spiral. There it goes through blue, and it creates this spiral structure in a simulation of Andromeda. Again, these are all recent papers. Here's a flat picture, in case my movies didn't work, from Gomez, 2013, who is claiming that's the Sagittarius dwarf. Again, this is the position of the midplane changing with distance from the galactic center in the same kind of rings and slightly spiral rings that we see in the data from the Sloan Digital Sky Survey. This is a figure from that same Gomez paper here, and if you look at the red tells you how many kiloparsecs the midplane of the disk is displaced below zero, and above r b equals 0, and it gets bigger. These waves get bigger and bigger as you go out from the galactic center. This is our wave. Unfortunately, it's mirror image, so you have to read them going in opposite directions. And we go up like 70 kiloparsecs. Their first one down here is like, this is 170 parsecs would be up here. So, I mean, it's of the same order of magnitude of the disk going up and down as it is from their simulation. The positions of these are somewhat different. But, you could imagine that someone would be able to work out some sort of model of a satellite going through the disk that might match the wave pattern that we're seeing. Okay, so what does all of this mean? The first one is that the stellar disk, according to us, does not fall off drastically in density 15 kiloparsecs from the center of the Milky Way. It goes out at least to 25 kiloparsecs, and the reason that people think that it falls off is that they're looking out there and the star counts go down, but the star counts are going down not because the star counts are going down, but because the disk moved away and now you're a higher exponential scale height from the plane of the disk. And so it looks like they're falling off, but it isn't really. Okay? So it makes the stellar disk much larger for the Milky Way. And in fact, all measurements of the scale length need to be reinterpreted because whatever data people were looking at could have been going up and down and kind of messing up that measurement. It could be that the spiral structure is driven by Milky Way satellites, whether they're dwarf galaxies or subhalos. And if you talk to people that simulate these, they have to be kind of the larger dwarf galaxy, not the I call them the pathetic dwarfs, the ones with one giant star, you know, these really low surface brightness things who are found in the Sloan. They have to be some of the large, so larger ones going through can excite this kind of stuff. Smaller ones don't. In fact, you could try to find out how many and where. You imagine, I don't know how to do this yet, but you can imagine trying to use these waves in the disk to figure out what's going through it. Are there any of these dark subhalos that the models predict are there in the halo of the Milky Way? Okay, so in conclusion, what I'm saying is we find an asymmetry in the star counts of the disk that oscillates from the north to the south to the north to the south as you look out towards the galactic anticenter. What we called the near north, that's probably a horrible name, but the near north structure is like 10.5 kiloparsecs from the galactic center and perturbed about 70 parsecs above the plane. The south middle is 14 kiloparsecs from the galactic center and goes 170 parsecs below the plane. The next oscillation appears to coincide with the Monoceros and triand rings, third and fourth Monoceros and triand, and those are going to be bigger oscillations, okay, as you go farther out in the disk. The rings open in the direction of the spiral arms, as far as I can tell, and I don't understand the distances any better than anybody else as to where exactly the spiral arms are, but it appears to roughly possibly match up with spiral arms, but the displacement is not as large for the spiral arms and appears to be in the opposite direction. And the observations are reasonably consistent with the predictions of infalling dwarf galaxies or subhalos in exciting these vertical displacements of the Milky Way's disk. And I'm going to stop there. Hopefully I didn't lose you guys. Take questions.